Meeting is being recorded.
So last time we were discussing the work done by a force, and we said that the work done by a force is given by Fd cosine theta, and if I have multiple forces, I can write these as, I can find the net work done on them, namely W net is either F net dot D, or I can write W net as the sum of the work by the first force, second force, third force, and so on. And then we defined the work energy theorem, which links the work done by a force to the amount of change of kinetic energy. So we said the net work done on an object is equal to the change in kinetic energy, which is half mv squared minus half mv0 squared. So this can also be written as W net equals delta K. This is the work energy theorem. It links the work to the kinetic energy. Now, one thing you should notice is if the network is positive, this means the kinetic energy is increasing and thus the speed is also increasing. You can take a look at our formula again. W net equals delta K. If this is positive, then K final is greater than K initial, and thus the speed is increasing. So when the network is positive, the speed increases. When the network is negative, the speed is decreasing. I will work on an example on a problem so we can reinforce the concepts of the work energy theorem. I have a proton, it is being accelerated along a straight line at 3.6 times 10 power 15 meters per second squared in a machine. So I'm given the mass of this proton, 1.67 times 10 power minus 27, and its acceleration, the proton has an initial speed of 2.4 times 10 power 7 meters per second and travels a distance 3.5 centimeters. What is its speed and the increase in its kinetic energy? So we want its final speed after it has accelerated and moved by 3.5 centimeters. So what we want is basically V final and K final. So what I can do is I can use the work energy theorem. I'll say W net is equal to F net dot D. Now I don't have the net force, but what I can do is I can write F net as M times A. So I have the acceleration, I have the mass. And I have the distance. I can find the network acting on the proton. This is going to be 21 times 10 power minus 14. The unit is joules. And now I will use the work energy theorem, which says that W net equals delta K. I have K initial. This is half mv squared, which is half times 1.67 times 10 power minus 27 times V0, which is 2.4 times 10 power 7. I can calculate that. This should be 2 times 10 power minus 20 joules. Oh, I forgot to square the speed, so let me fix that. So this should be 4.8 times 10 power minus 13. So now I'll just rearrange. Delta K is K minus K0. What I want is I'll solve for K. So K is going to be W net plus K0, which is 2.1 times 10 power minus 13 plus 4.8 times 10 power minus 13. This is equal to 6.9 times 10 power minus 13 joules. This is the final kinetic energy. We can deduce the speed. So this is basically half mv squared equals 6.9 times 10 power minus 13. So v is none other but 2 times 6.9 times 10 power minus 13 over the mass, which is 1.67 times 10 power minus 27 with a radical. This is going to be radical 8.3 times 10 power 14 which is 2.9 times 10 power 7. The unit is meters per second. So this is the speed. The increase in the kinetic energy is just delta K itself, which is equal to W net itself, which is 2.1 times 10 power minus 14. Now, there's one nice thing I want to notice in this problem before we move on. This problem could have been solved simply using kinematics, which we took in chapter 4. So here I could have said, or simply v squared minus v0 squared equals 2ad. And then v squared is just v0 squared plus 2ad. And we have v0, 2.4 times 10 power 7, plus 2 times A is also given 3.6 times 10 power 15 times D, which is 3.5 centimeters, and you will get the same answer. This is because essentially the work energy theorem is derived from the kinematic equations. Like we have multiplied by half times m here, and we are able to obtain on this side the formula for W net. So these two are actually derived from each other.
This meeting is being recorded.
Now, today I'm gonna be working on the second section of this chapter, which is on potential energy. We've talked so far about the energy carried by an object when it's moving, and we said this motion is associated with a kinetic energy, and this is proportional to the mass of the object and the speed. However, sometimes we can have stored energy in objects, even if they are not moving. Namely, you can see here, the arrow, once it is pulled on this string, it stores some energy such that once you release the string, the arrow immediately moves, which means the arrow had some stored energy which it was able to convert into kinetic energy to generate some motion. So potential energy is basically an energy that is stored in the object, and it exists due to a certain configuration or a certain position of the object. I'll give you another example. You hold a ball at a non-zero height above the floor, let's say at 1 meters. Once you release the ball, it immediately falls down, which means it had some stored energy. Whereas if the ball was originally on the floor, no motion, But if you release from non-zero height, it immediately moves. And you get some motion. This means that the configuration where a ball is at a non-zero height, at a position above the floor, gives it some potential energy. So the potential energy can exist due to a certain position or a certain configuration, such as the configuration here where the arrow is pulled against the string, then the arrow stores some energy as well. We're gonna differentiate between two kinds of potential energy, which are shown in these two examples. The first one is the potential energy stored from gravity. Obviously, here this ball falls down due to gravity, so the stored energy is associated with the gravitational force. We will call this gravitational potential energy. This exists during falls. In the second example, what I have is the string being stretched, and this I will name it an elastic potential energy. This is due to the bungee cord, the string here, a spring, so on and so forth. So anything that is stretched can store energy in it as it tries to restore its original length. I have a formula here similar to the work energy theorem. It says that the change in the potential energy is equal to minus the work done by the force that made it. So for example, for the gravitational potential energy, delta U, the change in the gravitational potential energy, I'll name this UG by the way, because it's gravitational, and this one, I'll name it U elastic. So the change in the gravitational potential energy can be written as minus the work done by gravity. This is our formula, which we will use to derive equations for the potential energies. So as you can see here, the gravitational potential energy, I can give it a formula, which is mg times the height y. This, I got it solely from here. I wrote delta U, the change in the gravitational potential energy, to be equal minus the work done by gravity. I substitute the formula of the work to be F times D, and you get this. You get mg times y. This is the potential energy stored in an object at a height y. Similarly, for a spring, the potential energy is equal to half kx squared. This formula comes from another formula, which is the force in a spring. So let me write this down. So in a spring, there's a force that is exerted on the spring, which is called Hooke's law, F of a spring, or the tension force. Sometimes we also name it tension. The force a spring exerts is equal to minus k times x. I remind you this is from forces, where k is the stiffness of the spring, and x is the elongation or compression of the spring. So if I tell you this spring is compressed by 2 centimeters, this is basically x. So for this force of a spring, the stored energy is going to be half kx squared. So k is the stiffness, x is how much we elongated the spring.
This meeting is being recorded.
So one important thing we have to be aware of is we have defined the potential energy to be equal to mgy. And we said y is the height of the object. However, when we measure the height of an object, I could be measuring it according to different references, and this gives me different results, by the way. Let's say I'm carrying a I would tell you this pen is 1 meters above the floor. And then you might tell me, well, maybe you're right, but I could also say this pen is 10 meters above the street. And both our answers are correct. So what we should do is, in problems involving gravitational potential energy, choose the ground to be y equals to 0, and choose what is your ground, you know? So you should say in all problems, let's say you choose your reference, so you show it in the figure and you write, this is where I take h to be equal to 0 or y to be equal to 0, and I will measure everything according to this reference. We see that in problem solving. It's very useful and important to make sure to keep this reference. Now, I'm gonna proceed with looking at our equations so far. So far we have said we have the work energy theorem, which is W net equals delta K. We also defined delta U to be equal to minus W net. Okay, but this, we said this work here is for the force generating the potential energy. So one thing I can deduce is if I don't have any external forces, I can equate delta K and delta U. So I'll write delta K to be equal to minus delta U. I deduced this from the two equations that I have made for the work energy theorem and the definition of the potential energy. So I combined these two, I got delta K is minus delta U, or I can also write this as delta K plus delta U equals 0. So if you add the change in the kinetic energy and the change in the potential energy, these two add up to 0 when, if the object has only conservative forces, so there's no friction, there's no external forces, then any change in kinetic energy should come from potential energy. I want you to see this example here. We are dropping these weights. As you drop the dumbbell, its height was a maximum, its height will decrease, so I know its potential energy should decrease. Now, as it also drops, its speed increases. It gains some speed, it is released from rest, by the way. Notice how my graph, the red graph, is for the kinetic energy. It starts from 0 and starts increasing, whereas the potential energy is decreasing. This is because the change in the kinetic energy is coming from the change in the potential energy. But if you add these two, the potential and the kinetic energy, they always have a constant sum. This constant sum, I will name it the mechanical energy of the system. So I will define the total or mechanical energy of the system to be the kinetic plus the potential energy. And I will say, if I don't have any lost energy and no external forces, then I can say that delta K equals minus delta U, and thus K2 plus U2 equals K1 plus U1. I can write this as the total mechanical energy, E mechanical 2 equals E mechanical 1 when all forces are conservative. Just a small comment on what I mean by conservative forces. These are forces which will conserve the energy independent of the path taken. So I'll write this as like no friction and no external forces. So let's say I'm pushing a block with my hand. This is a non-conservative force. So the mechanical energy of my system, which I defined to be the potential plus the kinetic, is going to be constant. You can see here I have an example, which is this pendulum. The pendulum is swinging, all right? When it reaches its maximum height, which is over here, its potential energy is maximum, its kinetic energy is 0. When it reaches the minimum height, which is here, this is the minimum height. Here, U is 0 because there is no height here, and K is max. Whereas at the maximum height, which is over here, this is the maximum height point. Here, U is max and K is 0. So what I want you to understand so far is the kinetic energy of a system can be exchanged with the potential energy, where the potential energy increases, then the kinetic energy decreases, or the other way around, such that their sum is always constant. If all the forces are conservative, there's no lost energies. So, and we defined the mechanical energy. This is K plus U, and we said this is constant.
This meeting is being recorded.
One last thing that I would like to also define in our study of work and energy is the rate at which we are doing work, how fast we are doing work. So the force, which is work, sometimes can do this work very quickly. Sometimes it can be slow. You can see an example of demonstration here. In both situations, the amount of work done is the same, but in the picture to the left, work is done in a shorter time. Thus, we are going to define the power. The power is going to be the rate at which we do the work, how fast we do the work. And this power is going to be defined as the work divided by the time. So this is W over T. We can write W as delta K later on or whatever. You can see how in the first figure, because the object is being lifted faster, then I will say the power is larger. The SI unit for the power is watts, and the work here is in joule. Watts is basically 1 joule per second. I have some other units here. You can take a look at them. They are not SI units though, but just you saw them, you'll be just familiar with what they are. Now I want you to see one more thing I'm gonna do with my formula of the power. We know the work done is written as F times delta X, right? So let's substitute that here. Now, when we look at our new formula, we have delta X over delta T, which is none other but the velocity of the object. So another formula for the power would be F times V. So the power can be written as F times V, and this is basically an instantaneous power at a specific velocity, right? So we have now two formulas. It will depend on the given. You select one of the two. So overall, in this chapter, we have defined kinetic energy. We have defined the work done by a force. We talked about the net work done, which is the sum of individual works. We discussed the work energy theorem, which is delta K equals W net. And then we talked about the potential energy of a system, and we talked about the power. It seems I skipped the potential energy summary. Let me write that down. So we talked about potential energy, for which we defined two formulas. First, we defined delta U to be equal to minus W of conservative forces only. And we defined two types of potential energy: gravitational, which is mgh, and elastic, which is half kx squared. And then we talked about the mechanical energy of a system. That's the total energy, E equals K plus U. And we said we have a conservation law. The mechanical energy of a system is conserved if all forces are conservative. This means we don't have frictional forces or external forces. And thus I can write K initial plus U initial equals K final plus U final. We talked about the power. We said it's the work done divided by the time. The instantaneous power can be found also from the force and the velocity of the object.
This meeting is being recorded.
So we're going to be solving some applications on what we took so far. I have here in question 8 an ice block floating in a river. It is pushed through a displacement d, which is equal to 15I minus 12j, along a straight embankment by rushing water, which exerts a force F, which is 210I minus 150j. We want the work done by this force. Work done by the force. This is F dot d, right? Now, F is 210I minus 150j, and D is 15I minus 12j. So we have F and we have D. We want to find the work. Now pay attention. This is a scalar product. we talked about this before. The scalar product f dot d can be written as fd cosine theta, or I can write it as fx times x plus fy times y. This is how we find the scalar product in math. This is a product where you have two vectors which give you out a scalar number rather than a vector. So it has two formulas. I would use the first one if I have angles. I would use the second one if I have x and y components, which is the case here. I'm given unit vector notations, so I have x and y components rather than magnitudes and angles. So I'll just substitute fx is 210, x is 15, and here I have minus 150 times minus 12. So I can solve. You should get 5,000 joules. Notice how I don't put I and J anymore here. No, this is wrong, because a scalar product gives me a scalar, not a vector. Question.
This meeting is being recorded.
In this problem, I have the three forces applied to a trunk that moves to the left by 3 meters over a frictionless floor. So let's just draw the vector D, just to keep in mind that it is to the left. The force magnitudes are 5 newtons, 9 newtons, and 3 newtons. The indicated angle theta is 60. During the displacement, what is the net work done on the trunk by the three forces? So we want W net, which we can write as W1 plus W2 plus W3. Now W1 is the work done by the first force. W2 is the work done by the second force. Let's keep these as dot products so we can be aware of the directions. So I'm trying to find the net work done by finding the work done by each force. Now I will look at each force individually and find the work done by it. So F1 is to the left, as you can see. To find the work done by F1, I have its magnitude, which is 5 newtons, and I have the distance d, it's 3 meters. We still need to look at the angle between them. So this is actually F1d cosine theta. For F2, it's going to be F2d cosine theta 2. Let's name this theta 1. Here I have F3d cosine theta 3. So in addition to knowing the forces and the displacement, I need to know the angle between these. As you can see, F1 is to the left and D is also to the left. So the angle between them is 0. So here I'm going to put F1D cosine 0. Now F1 is 5 newtons. I'll substitute that. And D is 3 meters. So I'll substitute that too. For F2, F2 makes an angle 60 with the positive x-axis. So if I want to check the angle it makes with D, remember when you find the work done, you need the angle between F and D, not the angle with the x-axis. So I'll make a small sketch. This is F2, making an angle 60 here, and this is D. So what I want is this big angle, which is none other but 180 minus 60. So this is 120. Now F2 is 9 newtons and D is still 3. If you look at F3, F3 is vertically downwards, whereas D is to the left. So the angle between them is 90, which means that, and cosine 90 is basically 0. And remember, we discussed that any force which is perpendicular to the motion, such as F3 here, F3 is vertical and D is horizontal. When the force is perpendicular to the motion, it doesn't do any work. So this will cancel out to 0, and we can find the work done by the other two forces. This will give me 15. This, any cosine of an angle where the angle is greater than 90, the cosine of it will be negative. So expect to have a negative work done. So here you will get minus 13.5. If you solve, you'll get 1.5 joules. This is the net work done on the object. I want you to take a look at things conceptually, regardless of the math. Now, the math says that the work done by F1 is positive and the work done by F2 is negative. and the work done by F3 is actually 0. Let's look at the physics. F1 is to the left, and the displacement is to the left. This means that F1 supports the motion. Both have the same direction. F1 will support the motion of the trunk. It will contribute to it. Whereas F2, as you can see, it's sort of opposing D. D is to the left, but F2 is sort of to the right, rightwards, upwards. So it's not really supporting the motion of the trunk. And that's why I expect it to do negative work. Looking at the math, the angle will be more than 90, and then the cosine will give me a negative value. So you get negative work for F2. F3 is perpendicular to the motion, so it will not do any work, so its work is 0. You can see how the physics always matches with the math.
This meeting is being recorded.
In part B, we're asked, does the kinetic energy of the trunk increase or decrease? So here I'm gonna make use of the work energy theorem, W net equals delta K. So I found that W net is positive, so delta K is positive, which means that K final minus K initial is positive, so K final is greater than K initial, so K increases. So I simply looked at the sign and knew that the kinetic energy of this trunk is going to be increasing. So this trunk, it feels a force opposing its motion and a force supporting it, but the net work is positive. So the net motion of this trunk is in the positive direction, and the net work is supporting the motion, it's not resisting it. Let's take a look at this question. We have a spring and a block are pulled to x equals +4. I have a missing figure here. Just give me a second to get it.
This meeting is being recorded.
So we have a block and a spring system. I remind you, in a block spring system, we defined the energy stored and the work done. We said we have a potential energy stored in the spring, which we named the elastic potential energy, and we gave it a formula, half kx squared. And we also talked that this comes from the spring force, which is minus k times x. So what is the question? We pull the block to x equals 11 centimeters. This is basically in figure B. So we pull it by 11 centimeters and then we release it. How much work does the spring do on the block as the block moves from x initial equals +5 to x equals 3 centimeters? So we're applying different forces and we have different displacements happening. I remind you, the work done by the spring is gonna be minus delta U, right? And this is gonna be minus into half k x final squared minus half k x initial squared. So I can rearrange this to half k x initial squared minus half k x final squared. Now, we have different positions for the spring. We're told when the block is pulled to x equals 4, we apply a force of magnitude 360 to hold it there. We pull the block to x equal 11 and then release it. And then we want the work done from x equal +5 to x equal +3. So, okay, one thing I know is x initial is +5 centimeters and x final is 3 centimeters. My problem here in trying to find the work is that I don't have K. I don't have the stiffness. But to find the stiffness, I will make use of the first given. I am told that if the block is pulled by 4 centimeters, we apply a force of magnitude 360 newtons to hold it there. So this means that to make an extension by 4 centimeters, we need this force. And we have a formula for the force, which is minus k times x. So I can deduce k from this formula. F equals minus kx. So we're told that when x is 4, F is 360. So we can deduce k. Now I want you to notice something. This is a vector relationship. When I want to take directions, I will not put the minus sign. I'll just take magnitudes. This is because in all cases, look at the force. The force by the spring is to the left, whereas D is to the right. So already this F is a negative. There's a minus sign here, so F equals kx. So here I put a negative sign because F is to the left. Okay, so let's substitute. I got 360 equals k times 4 times 10 power minus 2. Perfect. I am able to deduce k. It is going to be 90 newtons per meter. So I'll just use that. Sorry, this is going to be 90 Newton per centimeter. So per meters, no, this is 9,000. I found K. I'll just plug it here to find the work done. So W is going to be half times 9,000 into 5 times 10 power minus 2 squared minus 3 times 10 power minus 2 squared. We can find the work done. This is going to be 7.2 joules. This is part A. In part B, we want the work done when moving from x initial equals 5 to x final equals minus 3. Now, I want you to notice something. My formula has x squared, so it really won't matter if x is positive or negative in here. So if x is minus 3, it will be the same as plus 3. W will also be 7.2 joules. We have x squared in the formula, so the sign doesn't matter. Notice how A and B only differ by the sign. Here we are going to x equals plus 3, here to x equals minus 3, but because I have x squared in the formula, it really won't matter to me. In part C, we want the work done when going to x equals minus 5 centimeters. So x final is minus 5, so it's as if we're going, I have stretched by 5, and then I went all the way back to compress by 5 as well. Doesn't matter, let's look at the math. Again, I'll have half k into x initial squared minus x final squared. So this is half times 9,000 times x initial, which is 5, minus x final, which is minus 5. This should give me, oh, okay. So notice something. I have here 5 squared minus 5 squared. This gives me 0 joules. Why is that the case? I'm studying the case where I'm elongating by 5 centimeters. In that case, the spring is doing negative work. And then I'm compressing by 5, where the spring is going to do positive work. So the negative and the positive cancel out, and you get the net work to be equal to 0. In part D, x final is minus 9. So again, same calculations. One thing I want you to notice is we will get negative work because we have more compression than elongation.
This meeting is being recorded.
In this question, I have a 5 kilogram. It moves in a straight line on a horizontal, frictionless surface under the influence of a force that varies with position as shown. So we're given a block, and we're given the variation of the force with respect to position. At different locations, the block is feeling a different force. One interesting thing we can get from this graph, I want to remind you, in any graph in physics, the slope represents what's on the y-axis over what's on the x-axis, whereas the area under the graph represents what's on the y-axis times what's on the x-axis. So if I have, for example, you from chapter 4, if I had velocity versus time graph, the slope here would be v over t, which is none other but the acceleration. So I was able to find the acceleration from the slope of a velocity versus time graph. Whereas the area, this is v times t, which is going to be the displacement or the distance covered. So we could find the displacement by finding this area. This is delta x. Let's look at our graph here. Our graph is force versus position. If you look at the slope, this is going to be f over x. This is meaningless. We don't have anything in physics which is equal to the force over the displacement. But if you look at the area, this is going to be f times x, which is none other but the work done by the force. So if you find the area enclosed by the graph, this is going to be the work done by the force. And that's what the question is about. We want the work done by the force as the block moves from the origin to x equals 8 meters. So all the way from here to x equals 8, basically we want all of the areas enclosed. Let's look at our graph. The areas will be the area between the graph and the x-axis, which is this, by the way. Notice how in this section, the force is 0, so there is no work done. This makes sense. So I don't enclose any area. There will not be any area enclosed when the line is on the x-axis itself. Now, let's see how we can find the area. This is basically the work done. To find the area, I will look at my graph. So simply, if you look at the area here, this area is a trapezoid. Me personally, I never memorized the area of a trapezoid. So what I prefer to do is I distribute or I split the area into a rectangle and a triangle. And I'll find the areas of the rectangle plus the area of a triangle. The third section is also a triangle already. One thing I will notice is my third part is in the negative part. It's below the x-axis. So here the force is negative, which means it's going to be resisting the motion and doing negative work. So I'm going to put a negative area for that. So here I'll put a minus sign since F is negative in the third area. So W should be negative. Because x is positive and f is negative, then they oppose each other. The rest is really easy. The area of the first part, this part, is simply length times width. The length is this value, which is fs itself. How much is fs? It is 10. So we are given the value of f here to be 10. From that, I can deduce the divisions. This must be 5, this is minus 5, and this is minus 10. So the length is 10 newtons. The width is this quantity here, which is 2. The second area is height times base over 2. The height is 10 again, base is 2, and I will divide by 2. The third area is also a triangle, so it's also height times base over 2. And the height is this quantity here, which is 5 newtons. The base is 2 again, divide by 2, and I have a minus sign here. So I'll get 20 plus 10 minus 5. So this is 25 joules. So we were able to find the work done graphically from the area enclosed in the force versus position graph.
This meeting is being recorded.
So I'll solve a little bit from chapter 8, which is on potential energy. I have a small block of mass m equals 0.032 kilograms. It can slide along the frictionless loop. So the block starts from point P, it slides all the way down, and it goes through this loop. The loop radius is 12 centimeters. The block is released from rest. I'll pay attention to the word rest from point P. So V initial is 0. And point P is at a height equal to 5r. So this is basically H initial. I'll take my zero height to be over here. So this is H initial. This is not H initial, sorry about that. This is the reference of the height. I will take the height to be 0 at this level. What's the question? How much work does the gravitational force do on the block as the block travels from P to Q? So we want the work done by gravity. One way to think about it is, I'll just say the work done by gravity is minus delta U G, and minus delta UG is just mgh final minus mgh initial. I want the work done by gravity from point P to point Q. So H initial is 5r, and H final is the height at point Q. Look at point Q, the height is the radius itself. So I'll put r here. So I'll get 4 mgr, which is 4 times 0.032 times 9.8 times 0.12. You get the work done to be 0.15 joules. Now, one thing I want you to be aware of, you can always use this formula or use the work done by gravity is minus mg delta h. Like that's what I did basically. In part B, we want the work done from point P to the top of the loop. At the top of the loop, I'll name this point here T. Same formula. So in part B, I'll say W done by gravity is minus mg delta H, which is minus mg into the final height, which is at the top, minus the height at P, which is minus mg into the height at the top is actually the diameter of the circle, which is 2r, whereas the height at P is 5r, just as before. I'll get minus 0.032 times 9.8 times 2 times the radius, which is 0.12 minus 5 times 0.12. Then the work done by gravity is 0.11 joules. Notice how the work is positive. This is because we are descending. And when we are descending, gravity does positive work and it supports the motion. In part C, we want to find the gravitational potential energy itself. We want the potential energy at point P. So now we're looking for the potential energy, which we defined as UG equals mgh. To solve for gravitational energy, first choose your reference to the height. I chose the ground here to be where the height is considered to be 0, and I'll measure everything with respect to that. So we want U at P. This is going to be mg times 5r. And basically that's 0.032 times 9.8 times 5 times 0.12. And this is 0.19 joules. In part D, we want the potential energy at point Q. Point Q is at a height r. So this is going to be mg times r. Again, you calculate, you get 0.038 joules. Notice how this is less than the potential energy at P. Why? Because at Q, you are at a lower height. You store less gravitational energy than when you are very high at P. In part E, we want the gravitational potential energy at the top. So this is mg2r, which is 0.075 joules. In part F, we have a conceptual question. If instead of being merely released, the block is given some initial speed downward along the track. So we are giving some initial speed to the truck, to the block. Do the answers of A through E increase, decrease, or remain the same? So the thing here is, if you look at our formulas, U was 2mgr, W is mg delta H. Look at our formulas, all of them do not depend on velocity. So in part F, I'll say no velocity dependence. Why? Because at the end of the day, I'm interested in what the gravity is doing solely. I'm not interested in the effect of velocity and kinematics. The gravity does a certain work, and that's what matters. It only depends, like what the gravity does, depends on the gravity force itself and the heights. Same arrangement of heights, same potential energy, same effect of gravity. If you have a heavier block, for example, then that's a different story because the mass, as you can see, is a factor everywhere. So if I have a bigger mass, then I would have more work done. The mass does have an effect, and so on and so forth.